Welcome back. You're brave to go on. We're in the next chapter now. So let me pose this a question for you. Will drinking ocean water quench your thirst? If you hadn't guessed, the answer is no. And the reason is because the human body, on average, like the cytoplasm in cells in your blood plasma, it's 0.9% salt. So if we drink ocean water, we actually do not quench our thirst. But another thing, though, so salt water, ocean water is 3.5% salt, thereabouts. Depends on where you're at, but in general, it's about 3.5%. But also, if you have IV bags, you have to be very careful with IV bags. So if you see here, here's normal red blood cells. Uh, if you add something that's too salty, you get the shriveled up red blood cells. The water will leave the cells and it'll shrivel them up to get an equal amount of um, salt concentration. And if you put distilled water, you can get your red blood cells to burst. See, they can the hypo means less hypoosmotic. You can get the red blood cells to start to swell and even burst. So why all this happen? Well, this is osmotic pressure. So we're going to get into this and other things in this chapter. So we should start talking about some solutions. What is the definition of a solution? A solution is a homogeneous, both are proper or okay ways to say the word. I kind of switch back and forth, like either and either, I guess. But a homogeneous mixture of two or more substances, pure substances, and some definitions. Solvent is the most, and solute is the least. So the solvent is what does the dissolving. The solute is what is dissolved. So most of the time we think about liquid solutions, but there's other types of solutions. There's gas solutions. So air is a gas solution. You can get a gas dissolved in a liquid, so something like fizzy water. You can get two liquids dissolved, something like an alcoholic beverage, and you can get a solid dissolved in liquid like salt water. You can also have solid solutions, so things like different alloys of gold, for instance, so 14 karat, 18 karat gold. And just to illustrate this, the what's the solvent and what's the solute? So beer, I know there's other stuff in beer, but the percent alcohol is about 6%, depending on the beer. Water is 94%. Which is the solvent and which was the solute? For beer, the solvent is water and the solute is alcohol. But then if you go up, eventually you get to absinthe, which it can be 70% alcohol. Now the alcohol is the solvent and water is the solute. So it's just whatever you have the most of. And why do things dissolve? We're talking about this later, but I want to talk about it now. It has to do with something called entropy. Entropy is the amount of disorder. It's actually just probability. So it's plain old probability. We'll talk about it later. But the universe goes towards more disorder. So naturally, the universe is increasing in disorder. And there's two definitions for entropy. One is the reversible heat transfer over temperature. And also, you can calculate directly with the equation RT natural log of the number of states. The omega is the states. So RT, that's for the macro. For the individual states, you can use called the Boltzmann constant. The gas law R is just the Avogadro's number times the Boltzmann constant. So, and also gives us a definition. So the second law of thermo is entropy is always increasing. The third law of thermodynamics is that the entropy of a perfect crystal at 0 Kelvin is 0. And that helps the definition because a perfect crystal only has one state, and if it's at 0 Kelvin, it means it's not moving, that there is no entropy for that, meaning that there is only one state available, and that is occupied. So, and a solution forms, among other things, because the entropy increases. So, for instance, if you have this box here that I've drawn, if you release it, so you have neon and argon, I've indicated with dots as well. If you open the box, they mix, and they mix in an even fashion. And it all comes down to probability. It's much more likely for things to mix and become blended. So it's like, imagine if you have a jar of Skittles or something like that, like a colored candy. the Skittles at least that are colored, right? So if I took a bag of Skittles and I laid them all in the jar and I separated them by colors, what's going to happen if I shake the jar? Is the is it going to line up all nice and neat and even, or is it going to mix? And the probability says it's going to mix. Could it line up all nice and even? Like, yes, it could. Actually, that's possible. It's just very unlikely. And if that doesn't work for 200 Skittles, why the heck would it work for 10 to the 23rd particles, right? So something huge is just entropy just completely rules the universe that way. Good old probability. Okay, and a review from last semester, the different type of intermolecular forces. And there's the attraction between molecules, and the weakest being London dispersion, then the next highest, and generally speaking, is the dipole, then the hydrogen bond, then the ion dipole. And in general, if the so I told you entropy drives things, but also energetics do as well, the enthalpy. So if the solvent-solute interactions are greater than the solvent-solute interactions, I'm sorry, if the attraction between the solvent and the solute is greater than the attraction that the solvent and the solute has for itself, the solution forms. It also is exothermic. If the solvent-solution interactions are about the same as the individual interactions, the solution also forms. Among other things, it's driven by entropy. And then if the solvent-solute interactions are less than the solvent-solute interactions, it may or may not form the solution. And it depends on how unattractive they are to each other. But with that, though, later on, I keep on talking about later on, we're going to talk about what's called Gibbs free energy. And the delta G there, delta G, if it's negative, it means it goes. If it's positive, means it won't go. And you can see it's the delta G is equal to the delta H minus T delta S. So the temperature. So if the entropy is increasing at a high enough temperature, entropy will overcome this term, and it'll happen even if it's energy unfavorable. So you can get some things like that. That's things I don't necessarily like to mix, but if you heat them up enough, they will. And that's based off of the entropy, specifically the T delta S term overtaking the enthalpy attraction term. And in general, so this is a general rule, like dissolves like. So polars mix with polar compounds, nonpolar mix with nonpolar compounds, and nonpolar do not mix with polar compounds. And the reason, so like this graphic, I am using my limit of my artistic ability. Everyone probably knows that oil and water don't mix, and but to this oil molecule right here, it loves water. So good old electron cloud right here. It really likes water versus here's another like oil molecule. Oil molecules are long, and they're usually hydrocarbons, so they're a long hydrocarbon molecule. But the electron clouds they're like, well, there's this other oil molecule, and I can engage in, and so I'm a negative electron, and then I'm going to induce a dipole in there with my London dispersion force. Like, ooh, that's an attractive oil molecule. But you know what's much more attractive? Water. Water has this hydrogen bond permanent dipole here, and this electron cloud really is longing for that positive charge. And when the oil molecules, when you mix oil and water together, the oil's happy. Like, hey, I like that positive charge on your water molecules. Water molecules, though, they're like, hey, oil, you're getting in my way. I want to hang out with my other water molecules and form kind of a hydrogen bond network. And you've crashed the party. Get out. So the water actually pushes the oil out of the way, and because of gravity, the oil goes to the surface. So because it's less dense than the water. So yeah, water is kind of a jerk, pushing all the oil out of the way. So You think that oil hates water. Oh no, oil loves the water. Water hates the oil. And not only that, water's a bully. It pushes the oil out of the way. It's interesting how it works that way. Okay, so like dissolves likes. So let's talk about solubility with vitamins. So, uh, and what are vitamins? Vitamins are organic molecules that we need in small amounts. Organic meaning carbon containing. They used to be called vital amines, but we got rid of the word. We got rid of that when we found out they're not amines. An amine is a nitrogen-containing compound. So vitamin B5 here, this is an amine because it has a nitrogen there. So this is actually a proper vital amine. Vitamin C though is not a vitamin, is not an amine. But we since we found other ones, we just kind of dropped the amine. We said fast vitamin instead of vital amine. Anyways, here's vitamin C. And is this soluble? And generally speaking, chemicals tend to be either water soluble or fat soluble or lipophilic. So lipophilic means fat loving. Hydrophilic means water loving. So what is this? Is this water loving or fat loving? If something is water loving, that means that we can renally excrete it, and we need to eat it every day. Vitamin C has a bunch of these OH groups on it, and because of that, vitamin C is in fact water soluble, and you need to get vitamin C every day. You should get the minimum amount to get is 60 milligrams, but many dietitians believe that you should get 200 milligrams a day. So, and vitamin C, this is also known as ascorbic acid. So, anti-scurvy acid. So, vitamin C ascorbic acid is actually a common name. So, I don't know what the technical name for vitamin C is, but it is anti-scurvy acid. So, it is an acid. And it's very hard to overdose on vitamin C. Because you can renally excrete it, right? You pee it out. Okay, here's vitamin K, and if you look here, I've also drawn this as a ball and stick model over here. So if you there's the ball and stick model for it. You look at it. There's no hydrogen bonds anywhere. Hydrogen bond has to be with a hydrogen directly attached to an oxygen, nitrogen, or fluorine, and there's none of that here. So vitamin K is in fact fat soluble. And so your body can store it. So that means you do not have to consume vitamin K every day. And vitamin K is actually dangerous. So an overdose of vitamin K can cause coagulation. So too much vitamin K causes your blood to turn to something like cake batter, like a slurry. Too little vitamin K can cause hemorrhage, so you can start bleeding out your eyes and ears and that kind of stuff. Then again, if you have a patient that's hemorrhaging, the treatment for that patient is a megadose of vitamin K. And because of that, vitamin K is something that might cause an accidental overdose, and as such, you can only get vitamin K as a supplement with a prescription. So, but with vitamin K though as well, the plant-based vitamin K. I mean, there's a lot of vitamin K in spinach, for instance. And does that mean if you eat some spinach, you're just gonna your blood's gonna turn to cake batter? That's the difference between provitamins and vitamins. Provitamins is what your body will turn into a vitamin, but your body only converts what it needs. And vitamin K is an example. You can feel a little safe eating spinach. You're not gonna die from eating spinach. At least not. This would be very difficult. I guess you could die from that, but you have to eat a bunch and you'd burst your insides. Or you can choke on a leaf or something like that. But you won't die from the vitamin K, the provitamin K in spinach. But be careful though. Don't you won't find a supplement for vitamin K. Oh, and I should also mention about vitamins. One thing about vitamins is a lot of what we know about them are from their deficiency diseases. So we know what happens if you don't get enough, and we also, but it's hard to say if we're getting what we should. Here's vitamin A. So vitamin A, among other things, is an antioxidant. Oh, actually, I didn't talk about what vitamin C does. A lot of vitamins I didn't see you talk about before. Vitamin C is an antioxidant, which means it's a reducing agent. So antioxidant is another fancy word for a reducing agent. And what does vitamin C do? Like, well, imagine that I have a bunch of hungry fifth graders. So if I'm in my classroom and I have a bunch of hungry fifth graders coming to my classroom, and let's say I've got some spinach. Say I've got some spinach in my classroom that I do not want these hungry fifth graders to eat. Like, how do I prevent these children from eating my precious spinach? Well, if I got a bunch of Halloween candy and I stuck it in front of the spinach, like to distract the children, so the children will go and they'll eat all the Halloween candy, and then they'll be like, "Oh, we're full now. We don't want to eat the spinach. We're fine," and then they leave. So how do I avoid a very high energy free radical molecule that's extremely reactive? How do I prevent that molecule from attacking my cell's DNA? I don't want my cell's DNA damaged, and there's these free radicals that appear. How do I prevent that? Well, I put vitamin C in and around my cell, and then the free radical attacks the much more attractive antioxidant vitamin C, and it keeps my DNA safe. So that's what vitamin C does. It's our body's primary antioxidant. Vitamin A is also an antioxidant, but we also use it in our bodies for our vision. It's also known as, the name of the molecule is retinol. And vitamin C, the deficiency disease for vitamin C is scurvy. The deficiency for vitamin A is night blindness. You can't see in the dark if you don't get enough vitamin A. But anyways, vitamin A does have an OH group here, so it has some hydrogen bond network, but the rest of this is all a hydrocarbon. And because of that, vitamin A is in fact fat soluble. This one OH, just because something has an OH on it doesn't mean it's going to be soluble in water. Cholesterol is another molecule that's it's an alcohol, but it's very fat loving. And vitamin A is fat soluble. Also, vitamin A, you can get acute toxicity from vitamin A. Apparently, one of the best sources of vitamin A, so much that it'll kill you if you eat it, is a polar bear's liver. So apparently, polar bear liver is very rich in vitamin A. And if you eat a polar bear's liver, you will die from acute toxicity of vitamin A. So you can get too much vitamin A as well. But there is the provitamin for vitamin A is called beta carotene, and that is completely safe. You can eat so much beta carotene that it can turn your skin and your fat orange. So your body can hold that much, and it's not toxic. So stay away from the polar bear liver and eat more carrots. Let's take home with that. Okay, and then vitamin B5. Vitamin Bs, there's a whole bunch of them. They do different things. Vitamin Bs kind of help your nerve cells and your way that we process energy. Helps that work. That's a very loosely generalized description of vitamin Bs. But if you look at them, you have OH groups here. You got an NH group there, and another OH group. Oh, there's another one there. And because of these hydrogen bonding sites, vitamin B5 is in fact water soluble. And generally speaking, all B vitamins are water soluble, so we need to eat those in small amounts every day. So vitamin C and vitamin Bs, these are water soluble. Vitamin A, D, E, and K, those are fat soluble, so our body can store them. And I didn't talk about E. Vitamin E is the fat soluble antioxidant. It's like vitamin C, but it's for fatty tissues. And lack of vitamin E gives you kind of scaly skin, similar to scurvy. of sorts. Vitamin D deals with our body's ability to put calcium and magnesium in our bones. And the deficiency disease for vitamin D is called rickets, where your bones get very bendy. It's almost impossible to overdose on vitamin D or vitamin E. Vitamin Bs are very hard to overdose on as well because they're water soluble, but you can over time. So just because you can take some of these things you can take a huge percentage of vitamin Bs and Cs. That doesn't mean that you should do that as often though. That can cause other problems as well. So mega doses over a long term are a bad idea. So look at this molecule. This is beta carotene. Is it fat soluble or water soluble? It's fat soluble. I already mentioned that before. Let's look at something else here. This molecule is known as lysergic acid diethylamide, also sometimes called acid, also sometimes called LSD. Is this water soluble or fat soluble? And it has one NH group there, but for the rest of it, it is not water soluble. This is fat soluble, so this molecule can be stored in your body. And that's one thing with certain drugs. So certain cannabinoids, for instance, they can be stored in your body, and also like their chemical drug called PCP, that can be stored in your body as well. And PCP is dangerous because there's a phenomenon called a flashback, where if you're burning your fat, you can release the PCP back into your system, and then it can cause some of the effects of the drug. PCP is a category of drugs called dissociative anesthetics. So they disassociate certain sensations from what their function is. Well, especially pain. Ketamine is the same way. That's an animal tranquilizer. So let's say you break your arm and you take PCP or ketamine to deal with the pain. You still have the pain, but your body disassociates the pain sensation from its location being your arm. And that's dangerous then, because if you have a broken arm and then you're like, oh, I'm going to go use it and keep on using it, you can break it further, and you don't really associate the pain with the injury. So, but yeah. And also I mentioned storing drugs. So cannabinoids from cannabis, they can be stored as well. They can, in certain phenomena that people report. I personally have never taken drugs, so I just know it academically, I guess. But it's a phenomenon called reverse tolerance. So people that are habitual users of cannabis report that, like, well, it takes less and less and less for me to get my desired sense of euphoria. Why is there a reverse tolerance? And tolerance, generally speaking, if your body gets used to the amount of drugs that you're using, and then the effect goes down, so you need to use more and more. That's a phenomenon called tolerance, but seems to go the other way around for cannabis. And the answer is because your body's storing it. Your tolerance is going up, but your body just isn't getting rid of it, so it's still there. And then that's the phenomenon is from that. It's from the fact that the drugs haven't left your system yet. So, interesting stuff. Okay, last thing I'll talk about is the alcohols. So you can see here, methanol with one carbon. It is miscible. It means it's infinitely soluble in water. It means that it'll mix in any ratio. And but methanol also does not mix in hexane. So the hexane is nonpolar. And then ethanol. This is stuff that you drink for alcoholic beverages. Ethanol is strange because it's you can mix it with both water and nonpolar. So we put alcohol in our gasoline, for instance. So methanol sometimes goes in gasoline. So it's miscible in nonpolar as well. So ethanol is a interesting molecule. Same thing with propanol. So more frequently you see is isopropanol or rubbing alcohol. The rubbing alcohol drawn here, it just has the OH on the middle carbon instead of the end. But that's isopropanol. That's the rubbing alcohol. And of all these, I mean, you can drink ethanol moderately, I hope. But methanol you should not drink, and propanol you should not drink. I've never consumed propanol. Apparently, it gives you a very bad hangover. And methanol, if you drink that, you can get blinded from it. If it doesn't kill you, it can make you blind. Doesn't when it doesn't kill you, doesn't necessarily make you stronger. Butanol is with 4 carbons, and now we get to the point. You see the extra carbon chain that it's not very soluble in water, and pentanol is even less. But they do mix in fatty tissues, so they're fat soluble. Butanol is of particular interest because we're looking to use it as a fuel replacement. So because it's similar to gasoline as far as performance and that kind of thing. So we're looking at butanol as perhaps replacing gasoline one day as far as an alternative fuel. But we haven't quite figured out how to make it effectively in large quantities. So still working on that, but maybe in the future. And why is butanol looking at it? Because of the energy that's in it. Methanol's got 44% of the energy of gasoline. Ethanol has about 2/3, so 67%. So, meaning if you can drive 100 miles on a tank of gasoline, that means you could drive 44 miles on methanol. For ethanol, you could drive 67 miles, and then for butanol, you could drive close to 90 or 95. It's up there. And the so what with that? Well, can you imagine always having to refuel your gas tank? That would be an unfortunate thing. Also, on the U.S. mainland, they have the exits on the interstates. They're about 30 miles apart, and the reason why they have that is you can drive that in about a gallon with about a gallon of gas. So if your fuel light goes off in your car, you can usually make it to the next exit. But if that were the case with if you had a car on methanol, you'd get a lot of cars, at least before you train the drivers, a lot of cars would run out of fuel, which means they would have to build more exits between in the freeways, and that also has some environmental concerns there because now you start to have more human population centers, and that causes more environmental damage. So that's why butanol is looking as a replacement fuel for gasoline in the future, because that way we don't have to we have to build more communities. So interesting how those are from government think tanks, those ideas and data. Okay, and we're done with this section. We'll go on to the next section.